The main objective of this project is to analyze the different electrochemical processes and reactions that take place inside the battery electrodes during operation. To this end, we are using for the first time in-operando neutron scattering techniques. We are already placing real operating cells built using the same components as in the factories in a neutron instrument and collecting diffraction patterns and images from inside the cell, with both spatial and time resolution during the charge-discharge processes. We are using neutrons because its penetration capacity in matter is much higher than that of the other particles, as X-rays or electrons used until now in the analysis. In this way, we can study real thick cells in real operating conditions. This is an approach that has never used before in LED cells.
We will be able to acquire information on how the electrochemical reactions evolve in the cell electrodes in real time, while the cell is being charged or discharged. This information will be obtained from the bulk of the electrodes, not just on the surface of the plate. We would also be able to quantify the composition of the active mass and its evolution in time, identifying the different chemical species such as lead dioxide or lead sulfate during the charge and discharge processes. This will help to better understand the electrochemical processes that take place and act in accordance. Thus, potential improvements can be detected. In this project, we are going to apply for the first time a cutting-edge tool that helps to understand better the different processes that take place in the lead battery. In this case, with information never obtained before. This could result, for example, in the discovery of more efficient battery production processes such as the active mass formation, or in the use of certain additives in new and different ways in order to enhance the performance of the lead battery.
The research project underway with INMA and Exide is helping to address the goals of the CBI technical roadmap by developing never-before-seen insights into the governing mechanisms of lead batteries at a molecular level. The 150-year-old technology still has plenty of room for improvement, and the novel techniques from this team will shed light on new ways to extend cycle life by accurately describing how lead battery electrodes evolve during use.
This project will be beneficial in understanding some unsolved aspects of lead battery fundamental science. Combining the scientific excellence of INMA with the expertise of the Exide Group demonstrates the benefits of cross-disciplinary project teams working on battery science. There are many different possible neutron experiments to be used to understand lead battery technology. Europe has a strong base of scientists and funding programs that could support the development of better European-made lead batteries.
There are clear goals from the EU to decarbonize and decrease the reliance on fossil fuels. Understanding the fundamental contributors to lead battery failure at a molecular level will enable stronger cycling performance of lead batteries in all applications, such as microhybrid and energy storage applications. Batteries in these applications serve as the main tool to decarbonizing the European utility grid and automotive fleet, the most important areas underpinning the EU Green Deal.